So in this lecture, we will discuss how to design our slab for movements on ETABS software. A slab is essentially a beam or a flexure member. So slab is a flexure member. The difference between beam and a slab is beam is one-dimensional member, whereas slabs are two-dimensional members. So slabs are usually much thinner than beams. So slabs are much thinner than beams, which will have lesser depth compared to beam. So slabs are analyzed and designed as a series of parallel strips, each having a width that is 1 meter wide beam. So slabs are usually designed for a width of 1 meter. So at the end we will arrive area of steel in such a way that mm square per meter. Okay. So in slabs, shear stresses are usually very low. Shear reinforcement is not provided in slabs. So shear reinforcement is not provided in slabs. So we remember VU equals VC plus VS. So in case of slabs, VS is 0. So entire shear force, it will be resisted by concrete only. Okay. So we shall see some of the code clauses. First we shall see what is the minimum reinforcement. Minimum reinforcement. So for slabs, it is 0.12% BD. So if you refer IS 456 2000, page number 48, clause 26.5.2.1. So let me open the code. So IS 456, page number 48. Page number 48. See here. Minimum reinforcement. The mild steel reinforcement in either direction in slabs shall not be less than 0.15% of the total cross-sectional area. So if you are using mild steel, so it will be 0.15% of total cross-sectional area. So this is for mild steel, and this 0.12%, it is for HYST. See here in the next sentence. However, this value can be reduced to 0.12% when high strength deformed bars are welded wire fabric are used. Okay, anyway, we will be using HYST. If your depth of the slab is 150 mm, so minimum reinforcement will be 0.12 divided by 100 multiplied by width of the slab. It is designed for 1 meter, and depth of the slab, overall depth, so it is 150 mm. So here it is 1000 millimeter. 1000 millimeter. So let me solve this. Zero 0.12 divided by 100 multiplied by 1000 multiplied by 150. So it will be 180 mm square. If you are using 150 mm depth of slab, so minimum AST it should be 180 mm square. Okay. Next we shall see maximum diameter. Maximum diameter. So it should be always 1 by 8 times D. So 1 by 8. So it is 150 depth of the slab. So 1 divided by 8 into 150. So it will be 18.75. If your slab is 150 mm thick, you can use a diameter, maximum diameter up to 18. Okay. So let me check this also. See here, it is in clause number 26.5.2.2, maximum diameter. The diameter of the reinforcing bars shall not exceed 1/8 of the total thickness of the slab. So this also mentioned in IS code. So clause number 26.5.2.2. So clause number 26.5.2.2. Okay, IS 456 2000 on the same page, page number 48. So this is the criteria for maximum diameter. So if your depth of the slab is 150 mm, you can use a maximum diameter of the bar 18 mm. You can provide 18 mm dia bars. You cannot provide 20 mm. You cannot provide 20 mm if your slab thickness is 150 mm, because the criteria says it should be less than 1 by 8 times the depth of the slab. So next we shall see spacing. So for which you need to refer page number 46, clause 26.3.3 of IS 456 2000. So if you open IS 456, page number 46, So spacing, see here, 26.3.2. Maximum distance between bars in tension. In case of slabs, the horizontal distance between parallel main reinforcement bars shall not be more than 3 times the effective depth of solid slab or 300 mm, whichever is smaller. Okay, so this is for main reinforcement. Whereas the distribution reinforcement, the horizontal distance between parallel reinforcement bars provided against the shrinkage and temperature shall not be more than 5 times the effective depth of a solid slab or 450 mm, whichever is smaller. So spacing for main bars, it should not be greater than 300 mm, your spacing. For distribution bars, you should not provide a spacing greater than 450 mm. Okay, before going to design of the slab, you should remember these clauses. Okay. Next, I will take you to ETABS. So if you open your ETABS software, so first you go to design, live load reduction factor. Here you should select no live load reduction. Okay, you click OK. You next run your analysis. Okay. See, once you run the analysis, first you should complete these steps: deflection check, next design of slabs for shear, then it has to be followed for design of slabs for moment or flexure. Moment is nothing but flexure. So these are already completed. Okay, so once you run the analysis, so open ETABS, go to design, concrete slab design, view bar revise preferences. Okay, so in this you should select design code as IS456-2000. Okay, so in this various codes are available. You should select IS456-2000. So for steel, material safety factor 1.15, for concrete 1.5. Okay, so let it be default values. Next, minimum cover for slabs, so clear cover for top it is 15. Okay, clear cover for bottom again it is 15 mm. Preferred bar size, here you change the bar diameter to 10 mm or 8 mm according to your project requirement. So I will change this to 10 mm. Okay. You just click on OK. Next, go to design, concrete slab design, select design combination. Okay. So you have created 4 load combination, 4 load combinations. So out of 4, 2 are for limit state of serviceability, 2 are for limit state of collapse. Okay. So design combination. So you should select 1.5 DL plus 1.5 LL and you move the same combination to right side. So in your design combination, you should select 1.5 DL plus 1.5 LL. So you just click on OK. So next, go to design, concrete slab design, select stories for design. Either you can select one story or you can select all the stories. Okay, you select all the stories, click on OK. Go to design, concrete slab design. Next, you click on this start design. Okay, so now I am in roof floor. So you go to, once you design, you go to design, concrete slab design, display flexural design. Okay, there are 2 methods. One is finite element method, another one is strip based method. First, I will take up finite element based method. So first I will take up FEM method. So here you select finite element based. Finite element based. Okay. So you always check this box, impose minimum reinforcing. What the software will do, based on the thickness of the slab, it will impose a minimum reinforcement. So minimum reinforcement is 0.12% BD. It will impose that percentage, that area of steel. Okay. So in reinforcing direction and location, so this is very important. You need to understand these. First, you switch on the local axis for slabs. You switch on the local axis for slabs. Okay, see here. So you know the local axis RGB. So red is your local axis 1, green is 2 and blue is 3. So this is 1 and this green is 2 and 3 will be out of plane. So it will be in gravity direction. It will be out of plane. So blue axis will not be visible in case of a plan. If you take 3D view, it will be visible on 3D. See here. So this will be your red 1, green 2, blue is 3. So go to plan view. So first you need to understand direction 1 bottom rebar. I will explain one by one. Direction 1 bottom rebar. So this is your direction 1. So bottom rebar will look like this. So this is direction 1 bottom. Okay. Next is direction 2 bottom. So I'll change the color, direction 2 bottom. So it will look like this because this is your direction 2. So this is your direction 2 bottom reinforcement. So this is bottom. Again you have top. Again you have top. See here. Top rebar direction 1. So direction 1 is, so this is your direction 1 top. Okay. Again you have direction 2 top rebar. So it will look like this. So this is top. You have 4 directions or 4 types of reinforcement and locations. So this is bottom 1 and 2 and this is top 1 and 2. Clear? So anyway, at the site we will not going to provide 2 layer of reinforcement. Okay. So you provide, whether if you refer SP34, if you open SP34 in case of slabs, so slabs are detailed in 2 ways, by using bent up bars and by using straight bars. Okay. In case of bent up bars, we will bend our alternate bars. Okay. We will provide reinforcement like this. So this is by using detailing by using bent up bars. Okay. This area of steel, it will counteract positive bending moment. Your sagging bending moment at mid span. Whereas this portion will counteract negative bending moment or hogging bending moment at support. So this is at support. So this positive bending moment, it will be at mid span. Okay. If you are using straight bars, then you provide bottom reinforcement like this in 2 direction, complete mesh in 2 directions. So this is your bottom. For the top, we will provide only at the supports. We will provide only at the supports to counteract the hogging bending moment. Okay. So either you can use bent up bars or straight bars. So this is detailing as per straight bars. Okay. So You just click on this impose minimum reinforcing and you first select bottom rebar direction 1. Here you select, at the first step you select none, you click on apply, OK. See, so this is the reinforcement requirement bottom rebar. It is in mm square per meter, direction 1. Okay, so if you see the contour, it is showing its requirement. At the midspan you have greater requirement for bottom. So here you have selected bottom rebar intensity. Okay, over the supports you have no requirement. So you just click on design, concrete slab design, flexural design. Okay, next you select typical uniform reinforcing specified below. See here, bottom rebar. Here in case of bottom you select 8 at 300. I will take up this slab 8 at 300. You just click on apply. OK. See here, this slab, if you provide 8 at 300 mm center to center, this slab requires additional 12 mm square, 12.33. See here, if you move the cursor here, it is showing a additional requirement 12 at 12.33 mm square additional, which means this is not sufficient. This area of steel, it is not sufficient. So okay, instead of 8 at 300 you go to design, concrete slab design, display flexural design. You change this spacing to 250. Now if you move the cursor, see here, it is showing 0. So direction 1 bottom rebar. So direction 1 bottom, it is satisfied at 8 at 250 mm center to center. Okay, we shall see direction 2 bottom rebar. You select this one. Initially you select none, you click on apply. See here, so this is along direction 2. Okay, so you select this option. Again you start with 8 at 300. You click on apply. See here, again it is not sufficient. It requires another 12.33 mm square. Okay, so you change spacing to 250. See here, now the requirement is 0. So you can conclude like this. So direction 2 bottom, so it is 8 at 250 mm center to center. So this is your bottom. Reinforcement. Okay, either you can use bent up bars or straight bars for detailing. Okay, if you select top direction 1, top rebar, you select none in the beginning. So for top, whenever you click on top rebar, your requirement only over the supports. You need steel only over the supports area, not at the midspan. So this is direction 1 top rebar. If you select direction 2 top rebar, see here, your requirement only over the supports, not at the midspan. You need to provide the steel over supports. Okay. So next we shall see the top reinforcement. So direction 1 top rebar, again you select typical uniform reinforcing specified below. You start 8 at 300. See here. So it is satisfied. Again you check direction 2 top rebar, 8 at 300. See here. No requirement. So which means, so this is bottom reinforcement. So top reinforcement will be 8 at 300 mm center to center along direction 1, along direction 2 also same, 8 at 300 mm center to center direction 2. Okay. So this is 150 mm thick slab. If you check the thickness of the slab, so this is 150 mm thick slab. 150 mm thick slab. So minimum area of steel you need 180 mm square. Minimum area of steel you need 180 mm square. So whenever you check the contour, direction 1 bottom rebar, you just click on none, apply. If you move your cursor, see here, the requirement, it is showing minimum 180. Whenever you select this impose minimum reinforcement, so the software will automatically calculate, 0.12% BD. So minimum requirement is 150 mm square. In the slab, if your requirement is less than 150 mm square, it is still showing 180 mm square. 180 mm square, because you selected option minimum, impose minimum reinforcement. If you remove this option, you see the change. If you remove this impose minimum reinforcing and you click on apply, see here, now it is showing different values. It will not show this percentage, 0.12% BD. So you please remember, whenever you design slab, you should check this option, impose minimum reinforcing. Okay, so you select impose minimum, apply, okay. So for all the slabs you can check at once. You go to design, concrete slab design, display flexure design. See here. First I will select direction 1 bottom rebar. So 8 at 300. See here. So this slab, you move, if you move your cursor, yes, still there is a requirement. Still there is a requirement. I will change this to 250. 250. See here, 8 at 250. If you move your cursor on these 4 slabs, yes. So for these slabs, 8 at 250 is sufficient along bottom 1, along direction bottom 1. But these two slabs require additional, for which you can change the thickness. Instead of 200, you click to 250, you check with 200. Yes, it requires additional, so you check it with 175. Yes, this slab passed for a reinforcement 8 at 175 mm center to center. So bottom direction 1. Okay, whereas this requires additional, this slab requires additional. So you, instead of 175, you click 150. See here. So this slab passed at 8 at 150 mm center to center, bottom direction 1. Similarly, you need to check all the 4 directions. Okay. Okay. Next, go to display force bar stress diagram. You go to shell stresses combination 1.5 DL plus 1.5 LL. You select M11. You click on apply. Okay. See here. So this is your M11 bending. So I will manually check this. So here it is 4.7. So here for this slab, M11, which will be 4.75 kilonewton meter. Okay, per meter. 4.75 ultimate moment. So this slab, so you go to display undeformed shape. If you click on geometry, what is the thickness of the slab? Yes, 150 mm. The thickness of the slab, it is 150 mm. Your grade of concrete M25. Your grade of steel Fe, Fe 500. Okay, so we shall calculate the AST. So AST equals 0.5 FCK divided by Fy into 1 minus square root of 4.6 into mu divided by FCK BD square into B into D. So we need effective depth also. So 150 minus cover 15, first layer 10, second layer 10 by 2. So effective depth it will be 150 minus 15 minus 10 minus 5. So it will be 120. So effective depth 120 millimeter. So your AST will be 0.5 25 divided by 500 into 1 minus, so 4.6 into your mu is 4.75 into 10 power 6 divided by FCK 25 B 1000 into D. So D will be 120 again 1000 120. So if you solve this equation, 0.5 multiplied by 25 divided by 500 into 1 minus square root of 4.6 into 4.75 into 10 power 6 divided by 25 into 1000 into 120 multiplied by 1000 multiplied by 120. So here it is 120 square. So it is 120 square. So 0.5 FCK 25 divided by 500 into 1 minus here this equation AST equals 0.5 FCK divided by Fy 1 minus square root of, again here 1 minus 4.6 into mu divided by FCK BD square into BD. You just correct it. Solve once again. 0.5 into 25 divided by 500 multiplied by 1 minus square root of, again 1 minus, so 4.6 into mu is 4.75 into 10 power 6 divided by FCK 25 into B 1000 into 120 square into width 1000 into depth 120. So it is 92.46. So AST it is 92.46 mm square per meter, because your moment is 4.75 kilonewton meter per meter. So this is the area of steel required. So we will check. So you go to display shell stresses M11. So this is the location, 4 point, this location at the center. Okay, you go to close. Next you go to design, concrete slab design, display flexural design. You just uncheck. So your moment is M11. So direction 1 bottom rebar. Here you select none, apply. Okay. So see here, at this location, your steel requirement is around 100. So your steel requirement is 100 mm square per meter. So almost a similar answer. Okay, this region I took M11. At this region. M11 is 4.75 kilonewton per meter. For this moment, your area of steel is 92.46 millimeter square per meter, because as per IS code you need to provide minimum of 0.12% BD. You need to provide this as your minimum steel. So minimum steel is 180 mm square, your requirement, whereas actual requirement is 92. Minimum requirement is 180. So at the end you should provide minimum 180. If you provide 92, then it will be not correct, because code says there should be a minimum of 0.12% of steel. So you just click on design, concrete design, display flexural design. When I uncheck this, here it is showing area of steel as 100 or 110 something. If I click this impose minimum reinforcement, so it will include this 0.12. So you click on apply. Okay, now see here, it is changed to 180. So which means at this area, at this location, at this area, your actual steel was less than 180. So the code suggests to use minimum 180 mm square, but actual is less than 180. So we shall see the similar calculation for this slab. First we shall check the thickness of the slab. So it is also 150 mm. We shall first extract M11. So M11 for this slab. So you go to display, M11. Yes, I think it is, what is the maximum value? We will round off this value to 14 kilonewton meter per meter. Okay, so if you convert this value, it will be 14 into 10 power 6 Newton millimeter per meter. Okay, so here you change the mu. So mu is, instead of 4.75, you use 14. Okay, everything remains the same. FCK, width 1000, FY 500, effective depth 120, everything remains the same. So it is 281.54. 281.54 mm square per meter. So this is M11 steel. Okay. So at this location, so you go to design, concrete slab design, display flexural, direction 1. You beginning, you remove this, you click on apply. Okay. See here. Here it is showing 312 mm square per meter. So you go to display, design, concrete slab design, display flexural design. So this is how you can cross check your answers. Either you can extract MU, moment values, from ETABS and calculate the steel by using IS code equation, or you can directly use this option. Go to design, concrete slab design, flexural design. If you use this equation, show rebar above specified values. From this you can arrive the diameter and spacing also. Okay. Whenever you select bottom here, you should select this reinforcement. While you select top rebar here, you need to refer this. Okay. There is a chance of doing mistakes. Here you select top and here you select bottom. So this is wrong. If it is your reinforcement is top, your typical uniform, this should be also top. If it is bottom, here also you should choose bottom. Okay, so this is about finite element based method. So we will discuss strip based method also. So for which first you unlock your model, you go to draw, design strips. So you select width of the strip as 500 on both sides. Then the total width will be 1000. See here. If you have a strip like this, so this is your center. So this is your start and this is your end of the strip. See here. Start with the left. So at the start it is 500. Start with the right. So this width. Start with the right 500. End with the left. So this is also 500. End with the left right 500. Then total width of the strip. Total width of the strip, it will be 1000 millimeter. Okay. Initially you select strip layer as A. So your your horizontal strips as A, and your vertical strips vertical strips as B. So, okay, you go to draw, snap options, you select this midpoint, apply, okay. See here, now you can track the midpoint. Go to draw, snap options. See here, midpoint. You draw the strips like this. Okay. So horizontal strips are A and vertical strips are B. You run the analysis. You go to design, concrete slab design, start design. You go to again design, concrete slab design, display flexural design. Here you select strip based. Okay. Layer A is horizontal, layer B is vertical. You select any one first. You click on apply. Okay. See here. See here. In the beginning, we extracted M11 value and we found the area of steel as I think 90 to 100 mm square. See here, it is showing 106. Similar values. So whenever you check this impose minimum reinforcing, so it will include 0.12% of BD. Okay, you apply. Okay, see, automatically it is changed to 180. Your actual requirement is 106 mm square per meter, but code says minimum you should have 180 mm square per meter in your slabs. For thickness 150. This is for 150 mm thick slab. So these are your horizontal strips. You go to design, concrete slab design, flexural design. You can view vertical strips also, layer B. See here. Here you select typical reinforcing bars. See here, if you select 8 at 150, you start with the 300, 8 at 300. See here, it requires additional 12. You change this to 250. Yes, these two slabs are passed. If you select 200, not sufficient. If you select 175, see here. Again, this slab requires additional. So you 8 at 150. Yes. So like this. See here. Here you selected layer A and layer B, both layers. For bottom reinforcement, if you provide 8 at 150 mm center to center, all the slabs are passed. Okay. For layer A as well as layer B. So this is for bottom 8 at 150. Okay, this will be uneconomical because these two slabs are requires 8 at to 250, 8 at to 250. Instead of 8 at 250, you are providing 8 at 150 for these slabs. It will become uneconomical. Okay, so for the top also you can check like this. For the top also, see here you can check like this, 8 at 300. 8 at 300 is not sufficient. See here, it requires additional. 8 at 300 is not sufficient. It requires additional. You 8 at 250. See here, these are your additional area. You provide 8 at 225. Still it requires 8 at 200. Okay, 8 at 150. See here. So this is how you can optimize the design of slabs. So there are two methods to design the slabs. One is finite element based method. Another one is strip based method. So next class we will take up design of beams. So in post analysis, we completed deflection check, next design of slabs, that is for first for shear and next for moments, flexure design. So next we will take up design of in the next lecture we will take up design of beams. So after which design of columns. So last step will be your substructure, design of footings. So these are under post analysis.